We think about the clipbirds starting out on the whole island. We had this kind of distribution. What is it? It's flat. This is flat distribution. It wasn't even a normal distribution where we had a lot of medium animals and very few at either end. Maybe I should do that next time. I'll make it a normal distribution. On one side of the island, we had environmental changes, and in the end, we had a distribution that looked like this, with nothing, or we would have. While on the other side of the island, we ended up with a distribution like this. So it was a disruptive selection. You know, basically, on different sides of the island in different environments, the extreme versions of the trait were selected for. If you go enough generations with something like that, what you tend to end up, actually it was directional on each side, huh? It wasn't disruptive, it was directional. If they had stayed together, it would have been disruptive. So it was actually directional selection. I was wrong. End up with enough generations of that, and what you have now is two different species. If they sort of accumulate enough genetic differences, you end up with two different species. And we call this speciation. So we can say formation or creation of new species based on selective pressure. So the selective pressures on each side of the island change, the environment change, based on selective pressure. And to get speciation, to get a new species to form, you have to have a couple things. What's one of them? What did we have on the clipbird island? What do we have? We have to have isolation. We have to have some kind of isolation. Those populations have to be not interacting. And then we have to see natural selection pushing those populations in different directions, favoring different traits, selecting for different traits. And that's when we get speciation. We get the formation of brand new species. Okay, so with that, let's talk a little bit about the cheetahs. Cheetahs are sort of the classic example of this concept. At some point you had lots of cheetahs, maybe thousands of them, maybe hundreds of them. I don't know how many cheetahs, with all the kind of variation that you see in any population. I mean, look around at humans. How much variation do you see in humans? Lots of it. And you probably had similar levels of variation in cheetahs. So at some point, there is some catastrophic event, and I don't know what it was. I'll just make a big thunderbolt, lightning bolt here. I don't know. It could be disease. It could be, I don't know if it was an ice age thing. My husband and I were talking about ice ages last night. I'd have to look. I'm not sure what it was, but the environment changed radically. Most cheetahs died, and what you ended up with was a very small number of individuals. Those, and I believe it's estimated to be between 7 and 10 individuals, repopulated. Every cheetah on the planet is descendant of those individuals. So, think about gene pool diversity. Where is there bigger gene pool diversity? Here, before this calamity, or afterwards? Where do we have larger gene pool diversity? Oh yeah, before. We lost, they lost probably 99% of their gene pool. Hundreds of thousands, tens of thousands of years of evolution to create some of those genes, gone. So what you come out of it with is this really reduced diversity. This is now a founding population. Because founding populations work this way too. And so every cheetah on the planet, and I think there are a couple thousand cheetahs on the planet now, are descendant of those individuals. Anybody here know someone who's had an organ transplant? I bet you all do. Mrs. Thomas has had a liver transplant. When you have an organ transplant, what's one big challenge you face? Your body, your immune system recognizes that that organ is, basically your body has tags on everything that say me, me, me. And when something comes along that doesn't have the tag that says me, your body goes, not me, not me, not me, get it out of here. Which works really well against bacteria and viruses and foreign bodies like splinters in your finger, all those things. Great. It doesn't work so well when you have an organ transplant because there's no tag that says me. And, you know, someday in the future, maybe we will be able to actually change markers, immunomarkers on transplanted organs, so this isn't an issue. But until that day, what you're looking at is anti-rejection drugs for the rest of your life to suppress your immune system so that your body doesn't go, wait a minute, you don't belong here, get out, and reject the organ and kill you. So people who've had who've had transplants are at high risk of infection, like a cold can be fatal. They can't, because their immune system's suppressed for life. Cheetahs, every cheetah on the planet is so closely related that they have done skin transplants between cheetahs, and they don't require anti-rejection drugs. They are so closely related, they are so genetically similar that their bodies don't even recognize me, not me distinctions between parts from other cheetahs. They have got such limited genetic diversity. They are so alike. Tremendous similarity. Could also say very low genetic diversity. There's a very limited number of genes that cheetahs have. You can transplant skin and organs between two cheetahs, and they're so similar their body doesn't even recognize it's not their own. Yikes. What we call this, and this is a term that I did not include on your list, but I probably should have, is a genetic bottleneck. Okay? It's a genetic bottleneck. When you have some calamitous event that tremendously reduces the genetic diversity in a population, and then you have a very small founding population on the other side of that, so then your resulting recovered population has really low diversity, that's a genetic bottleneck. Why is that a bad thing? Great, all cheetahs are alike. They can do skin transplants. Cool. That would make life easier for a lot of transplant patients. Why is this bad? Why is it bad if everybody's alike? Why?
Because if someone comes along, there's less likely to be a more helpful trait somewhere.
Okay, if everybody's alike, the thing that's fatal for one is fatal for all. So here's the deal. Cheetahs are beautiful. Cheetahs are cool. I love watching videos of cheetahs running. Oh my gosh. I mean, they're off the ground more time than they're on the ground. They're amazing animals. They will probably go extinct no matter what we do. Conservation efforts aside, and there have been massive conservation efforts on the behalf of the cheetah, because they've faced a lot of habitat loss. They've faced a lot of the normal kinds of pressures that humans put on wildlife. Despite anything that we do, cheetahs are probably going to die out and go extinct. There is such low genetic diversity among cheetahs on the planet that their population, their whole population, not just isolated populations, are so susceptible to everything and anything. They're just not very resilient. There have been other cases of this. But this is kind of the classic. There's a worrisome one with sycamore trees right now, where they've found that sycamore trees in the U.S. Do you know what sycamores are? They've got the like really funky, multicolored bark, and they're lumpy, and they have big sort of mapley looking leaves. Very low genetic diversity because most sycamores in the U.S. are planted nursery stock, and they're cloned. They're actually cloned from a very small population of trees. So I think I just read something that said like all the sycamore trees growing on city streets in the U.S. are for the most part the descendants of 3 or 4 individuals. Because they were just cloned. Because it's an easy way to reproduce plants. Well, sexual reproduction gets you diversity, gets you mutation, gets you new genes, gets you new traits. We don't have that. So if a disease comes along that affects sycamores and it affects those sycamores, they're all done. we lost our chestnuts, we lost our elms, or we're losing our ash trees, diversity matters. Having a lot of different genes really makes a difference. It allows a population to evolve in the face of hardship. Okay, that's genetic bottlenecks in a nutshell. I'm sorry, that was rather depressing, wasn't it? That was really kind of, hey, look at these beautiful, cool animals. They're all going to die. Sorry.
You're just gonna get better.
I know. I'm so sorry. We try to do happy stuff, too. So you might want to add genetic bottleneck to the bottom of the vocab. Some of you I see are busily working on Part C for things. You should probably have some notes on this, though, too.